he takes this, K of H1, H2. Then F over L is a delta field of genus 1, and he shows that it has no movable singularities. By a tour de force of equations, the analog of what I did in Mumford's non-example, by choosing local coordinates at infinity. But it really is a beautiful 2 pages in his book. And so this is the thing which he would be strongly not. So he always thought that, by what do I do for an algebraically completely integrable system with spectral, with invariant manifolds? For example, a C2 over lambda, a Jacobian of a genus 2 curve. He always thought, oh my God, I have to redo all this, this piece of cleverness. And then my stupid me walks in and says, but everybody says that algebraically completely integrable means that these functions are complete at infinity. So he starts thinking about just a field of functions, and he says, oh yeah, it's gonna work. We haven't written it up. But the statement should be this, that if we have that kind of very careful algebraic complete integrability where the integral manifolds are tori, and Mumford tells you it's algebraically completely integrable only if these fields don't have poles at infinity, then we can conclude strongly normal. That seems to be the case, because we went through a few Lux pair equations for genus 2. But now I'm going to tell you where the fun begins. The A, have you forgotten the A? Can you dare to forget the A?
How many decades ago?
So when we were discussing this, I think for the first time, due to my stupidity, Alex realized that A was anything in K. So it's possibly a transcendental. So there is possibly a conformal deformation. There is, because he wrote it. There is a conformal deformation, which is, the A is just in K minus 0. So it doesn't have to be in C or in the field of constants.
But the invariant is the two invariant.
Is it invariant under the
nothing to
derivative?
do with A.
The A is in derivative. So it's a conformal deformation of the derivative. That's how we view it. Okay, so now the fun begins. So we thought, okay, so now we take a spectral curve of genus 2, and not having time to show you an ACI of genus 2 that arises like the tau. I'll just tell you that the equation of the curve, instead of being y squared equals a times x minus c1 times x minus c2 times x minus c3, like in this case, it's going to be x minus c4 times x minus c5. Okay, so there's such an example with Lux pair, with all these integral manifolds being Jacobians of genus 2, and we were all excited that there may be an A, which can be non-constant in the strongly normal extension. And then all of a sudden, Alex writes me an email and says, oh, but I noticed that if you have two derivatives, d1 and d2, not just one delta, and if you want AD1 and AD2 to commute, then D1 has to be equal to D2 equals 0. That's a one-line exercise. So at the moment, we may not be able to construct a conformal deformation of the vector fields of the derivative in the genus 2 case. And I think it's fun because I still hope that there is a deformation somewhere. Geometrically speaking, there are examples of genus 2 ACIs that completely contain a genus 1 ACI, because each of the Jacobians has a torus inside. They are very special, but they exist. So what's going on? And that's something we're thinking about. And then the inverse Galois problem. So in maybe a minute, I wanted to tell you about this KP deformation. So this is in part 5, where the fun begins. This is puzzle number 1, conformal deformation of the derivative. And then puzzle 2, so this is what I wanted. So the KP equation is a PDE, and in some very special cases, you can show that the initial conditions are such that there is only a finite number of independent derivations that commute and that are called the KP hierarchy, and really not doing a good job of describing that from scratch. But anyway, and then the manifold to which they're tangent is the Jacobian of the curve. Okay, now in the KP equation, the KP solution can be written in terms of theta functions on that Jacobian, and this is where just an expression, not just theta itself, is the second derivative of log theta, and then the variables are the x, y, t in the equation. The equation, just is a PDE, so u yy equals u xxx, and you want it to be nonlinear to be interesting, so uxu plus ut, or let's normalize all the derivations so that it's just simply plus some x. And then this theta function of something plus a constant. This constant depends on the moduli of the curve. And so now you can change the curve in moduli and get solutions. And so I told Alex, but so can we have a Galois theory where this variety for the strongly normal extension will have, both Jacobians and the moduli of the curve. And so, okay, so let's be able to finish in a moment what the idea might be. I really hope it might work, but we're not claiming that there is anything yet. So in some very special cases, you can actually write an ACI. And for this ACI, these Jacobians will carry these KP solutions, and the base will be part of the moduli space of curves of a given genus. But you can write an ACI. It's very special. It's a completely different idea because, now you need a Hamiltonian system, but you carry these solutions along. So there are functions here. And so Alex at the beginning said, okay, now the problem is, when you want to think of this as a function field of something, You can make an ACI, but then these are the angle variables, right? And a little neighbor here will be called the action variables, okay? But you have to identify these action variables with a subset of, say, Cn or Rn. This identification map is not algebraic. It's very highly transcendental. So there I go. I found a paper by Veselov and et al., in which they are able to write the Gauss-Manin connection for these moduli with algebraic functions, starting with the functions of the ACI. And then they write the deformation of the base in terms of algebraic functions. It's called the Gauss-Manin connection. And it so is ad hoc that they can only do it for that system, which is a lax pair, and it happens to be the geodesics on the ellipsoid, I believe. And the reason they write it by brute force, they split the moduli of the curve in two pieces. The curve has that equation, okay, they say, okay, let's hold these fixed, and let's vary C3, C4, C5, and then we have the Gauss-Manin connection with algebraic functions in C3, C4, C5. So it really is a beautiful little piece of work that if one can do it, then can produce a strongly normal extension of these algebraic functions. So this is all very tentative, but because of who you are, I thought you might help with the ideas. And,
Do you have any reference for the last description?
do I have a for?
A reference for the...
For which one, the Veselov? With me. Yeah. You should see it.
Yeah.
You should see how they got the Gauss-Manin connection. They really, it really is incredible. So I had it, but then I had to buy because I didn't have time to take up everything. In a perfect world, this is yours.
Thank you.
You allow me to apologize for the disaster I brought upon you today. And you should.
Can I ask you, going back to Alex,
that
strongly normal is equivalent to weakly normal and NMS. Where does the algebraic integrability come in there?
The algebraic integrability is an extra property that you work through. Now let me think I think it's due to Kolchin. That once you have this, so this is, as far as I know, due to Alex. I mean, it's in his book, and he says, I want to compare the definitions of normality. And this, means this projective, being able to make the variety into something projective. And then Kolchin, in his one papers, says strongly normal means that the functions are algebraic, are abelian functions on Torah.
Yes.
And then Alex sees this algebraic complete integrability, and he says, wow, the extension is generated as a field, as a differential field by theta functions. And he says, okay, so let's go and check that the genus 1 case, the first case, is a strongly normal extension. And he had to construct this clever thing, this F slash L, this extension of the invariance, to show that he could complete it into something projective.
Well, what I was wondering is if you start with weakly normal plus NMS and allow any of Pan-Levet's NMSs, will you get an embedding into a strongly normal extension, or is it just some of his?
I would love to
The
understand.
algebraic integrability could be just some of it. Would it apply?
That would
Would it apply to all of his list of 54 or whatever?
No, so the NMS doesn't characterize Penlevic property as...
Right, exactly. So
So,
that's why I
no.
was wondering why you would get embeddability in a strongly normal extension.
No, but I think NMS is not the Penlevic property.
No, but what, would this apply to all of his list? Of Pan-LeVay's list of differential equations, ordinary differential equations with no movable singularities?
No, but that's what I'm saying. So the
That's-
new movable singularity
Right.
here does not correspond to Penlevic's list of...
Right. So, oh, just the others, you mean?
No,
No,
but
there's
she
no
means a
correspondence.
different. I think she means a
I'm just
different
wondering.
Penlevic. I think she's right, and I think it would be a great point of view.
Yeah.
So there is a Penlevic property, which means that when you expand locally,
Right,
you have these balances of the solutions,
Yeah.
right.
and if they work, is that what you meant?
Yeah.
But I think it does happen for ACIs. It was
For
proved.
ACIs, yeah.
Yeah,
For ACIs.
Yeah,
oh,
for ACIs.
Oh, you want any general?
Yeah,
exactly. Yeah.
I don't know.
No.
Yeah.
But that would be a different point of view in which we could think of the ACIs and
Yeah.
say, are they, if we take something Penlevic, does that give us strong normality?
No,
Are you
no,
saying
no,
no?
no.
Ah,
Yeah, no.
The outside strongly normal.
thank you, I didn't know that.
Yeah.
But
Yeah.
thanks for bringing in the Penlevic property.
Yeah, thank you.
It was great to have your questions and your attention. Thank you.
Do you have any notes on this?
No, I
Just thinking it through.
these text notes which are not finished, so I don't want to,
Yeah.
thank you. I would share them if I did.
No.
And I have too many deadlines to promise that I
That's the picture.
I understand.